So this is Sylow's theorem number 2. So let P1 and P2 be Sylow P subgroups. Now remember what that means. It means that the size of P1 and the size of P2 are the highest prime power that divides the group. In this case, there's an element in the group such that A1 inverse P2A is P1, meaning that P1 and P2 are conjugate. They're really kind of the same structure of the set. In fact, they're isomorphic. And the isomorphism is conjugation. So this is kind of an amazing fact. So let's prove it. We're going to prove it using group actions. So the set X that I'm going to use is the set of left cosets of P1. In P1 in the group. Now P1 might not be normal, but you could still look at the set of left cosets. It's a perfectly valid set. That's my set X. Let P2 act on X by this method. So if I take an element B, B is going to be in P2, and I take a left coset in X, so A P1, then I'm going to define this group action to be BA P1. So a perfectly valid group action. By our lemma proved in the last video, we know that the size of the set of elements in X that are fixed under anything in P2 is the same as the size of X working mod P. Now, the size of X, that's the number of left cosets in the group. That's the size of the group divided by the size of P1. So these are the same, mod P. Now, P1 is a Sylow P subgroup. That means it's a subgroup of the highest possible prime power that divides the size of the group. So the group is divisible by P to the K. So maybe the group, has size P to the K times N, where N has no powers of P in it. But P1 has size P to the K. So when I divide these two things, the P to the K's cancel, and I'm left with an N that's relatively prime to P. So N has no primes in its prime factorization of the form P. So that means this is not equal to 0 mod P. So in particular, this means that this set cannot be 0. It's non-empty. It's a non-empty set. So I could take something in it. So I could take an element A P1 in this set. Now let me remind you of what this set was from our lemma. This is the set of all elements in X, so everything of the form A P1, such that when I apply this group action, nothing changes. So B times AP1 is equal to AP1, and that has to be true for all elements B in P2. So I know this set is non-empty. I know there's at least one coset AP1 that satisfies this condition. What does this mean? this means that B A P1 is equal to A P1 for all B in P2. I just rewrote this condition down here because I want to manipulate it to look like A inverse BA P1 is P1 for all B in P2. So I just multiplied both sides on the left by A inverse. Now, in order for this condition to hold, this means that A inverse BA has to be an element of P1 for all B. In other words, this shows that A inverse P2, B was in P2, so if I take anything in P2 and do A inverse P2A, then I land back in P1. I get a subgroup of P1. But these two sets have the same size. Since these subgroups have the same size, this shows that A inverse P2A is actually equal to P1. That's the statement of the theorem. That's a statement of the theorem. If you have a subgroup of P1 that's the same size as P1, then it's got to be the whole subgroup. It's got to be the whole group. So there's a proof of Sylow's second theorem, again using the idea of group actions. All right, fantastic.